Our next speaker is going to tell us about capturing vegetation-water interactions in Earth system models. His name is Pierre Gentine. He's Associate Professor at Columbia University in Earth and Environmental Engineering. He received his PhD from MIT in 2010 in civil engineering. There's a trend here. He's interested in hydrological and carbon cycles, and he's been the recipient recently of a number of prestigious awards from the AGU and the Clarence Meisinger Award.
Thanks again for having me today. So it's a pleasure to be here. Lots of friends and lots of great people in the room. So I didn't know that would be that amazing, but that's a real pleasure to be in front of you. So I really wanted to maybe get back to some of the basics. So a lot of you you can sleep for maybe 20 minutes. I'll wake you up when you can wake up, like maybe at a time. But a lot of that I wanted to maybe get back to some of the basics so we can connect maybe to the measurements and get it back also to maybe some of the remote sensing data. So we'll try to go slowly into different things. So first looking at soil physics. Might be boring for a lot of you, but just to look back at what a porous medium is and how we will introduce Darcy's law, and also try to link basically pressure and moisture, because that's something we need when we want to look at remote sensing data. And then we look at xylem transport. So we've had some of that today, but looking at how the water is basically being transported from the soil to the roots into the xylem and the leaves. And then we look at leaf gas exchange and what are the different factors that are regulating leaf gas exchange. And then we'll talk about the role of water, and then try to actually go back down. So we'll talk about phloem. So it's not there yet in many of the models we have, but I think we are starting to actually see some of the development there. From Mancuccini's work, Gabby is also working on that stuff, and that seems very important, so we'll try to see if we can connect some of that. And then I'll mention things that are maybe at a more personal level, but I'll mention some of the scales in terms of temporal scales and spatial scales, and how we can actually maybe use that to our advantage, and maybe where that can be an issue when we want to connect the dots. So. And again, maybe some of the things will be very basic, so apologizing in advance. So really surface hydrology 101, so what is that? So what is really driving the flow? It's actually the total energy that we have. So in soil physics or in physical hydrology, we call that the hydraulic head, so that's this H here, which is basically a gravity term, so basically potential energy plus some internal pressure, which happens to be always negative, so it's a tension term that you have in the porous medium. And the reason that you have that is because of capillary effect. So basically you have the matrix of the soil and the soil grains that are actually pulling against gravity, which is basically what you can see here. You have basically at the interface between the soil grains, and you have three phases. You have the liquid, the air, and the soil, and that's going to create some basically surface tension. And that surface tension is actually very important because that can hold water against gravity. And so that's why that term here is going to be negative. And then you have kinetic energy, but you can basically drop that term because those flows are actually very, very small, or so you can totally neglect that. Okay, so that's basically what happens in the soil. And so hydraulic head is going to be what's basically driving your flow. And so it's not just about pressure, but it's also the gravity term can be important sometimes. Okay, so the typical, when we want to connect to water content, and that's going to be important when we want to look at plants as well, is we typically use this kind of meniscus analogy, which actually happens to be actually maybe a little bit better for plants than for soils. But what we do is we say we can have menisci of different sizes, so you can have different basically radii for those different menisci. And what we know is that the change in pressure, or the head that you will have here in the different menisci, is going to be basically inversely proportional to the radius that you have. Okay, so when you have a very high radius, what's going to happen is that the height that you're going to get there is going to be lower, and when you have a thinner tube, basically you can actually pull a little bit more. Okay, because the surface tension, so it's a kind of a perimeter, if you will, to area ratio, that's going to be more important on the right-hand side. Okay, so you can basically pull more on the right-hand side. Now what's going to be important is you can track the amount of moisture that you have. So the total moisture content that you will have in the soil is going to be all of the blue, or all of the liquid water that you have. Okay, and then you have the air space in between. So now what you can do is you can start recording. You can pull on that, and you can start recording what is the moisture content variation as a function of the pull or the tension that you have in your flow. Okay, that's going to be very simple. So you can record that. So on the x-axis here is you have the total amount of moisture you have. as a function of the absolute value of the tension, because that's negative again. And you can start pulling basically, and basically nothing will change. You will keep increasing here, and nothing changes that much. So basically the moisture content remains the same until you reach the large radius one, right? And then you will start draining that guy pretty quickly, okay? So you will start seeing that drop here. Okay, you can continue. Then you reach another stage where basically the moisture content remains the same. You pull again, and then again nothing happens until you reach the medium one, okay? And then you will start draining that medium one again, okay? And you can go on and on until you reach the smallest radius in that case, okay? And now you're going to be basically empty. Now, in reality, what we have is we have a pore size distribution, so we not only have 3 different radii here, but we have a continuum, and that tends to basically generate a curve that happens to be very smooth, something that looks like that. Okay, so this is called a retention curve. And what this is saying, and that's actually going to be important, is that there's a relationship between the moisture content, and that's going to be kind of similar but also different in plants, is that there's a relationship between moisture content and also basically the tension or the pull that you're going to have in the soil. Okay, and you can make the same analogy in the plants. There's going to be a relationship between relative water content, as Patrick was mentioning before, and basically the tension that you will have in the xylem. And that's going to be important because typically what's driving the flow is tension, but what we can typically measure more easily from space is going to be moisture content, okay, or the dielectric constant. So that's actually important. And you can go backward basically in that case. If you have this one-to-one relationship, you could also have psi as a function of theta. And of course, we mentioned that before, but you could have some hysteresis effect. So you could have actually some memory. So if you are actually refilling as opposed to drying, that could actually be different. And that happens to be very important in plants. That can also be slightly important in soil, but I mean, maybe more important in plants. You might have more hysteresis. So that line might actually not be a one-to-one relationship. That can actually maybe vary as a function of time and also as a function of space. Or state, sorry. Okay. So now that we have that, so we know what's actually driving the flow. So what we have in a porous medium is this law, which is called Darcy's law, which is saying that the total discharge, so basically the total amount of volume per unit time, that's going to, you can think of that, it's almost like a mass flux just multiplied by the density. That's going to be the discharge per unit cross-section is going to be related to what we call a hydraulic conductivity. So you can think of that, it's almost like a diffusion coefficient times the hydraulic gradient. Okay, so that's the gradient that we have in hydraulic head. Okay, and that's going to drive the flow, and so that's what we call Darcy's flux, which has units of a velocity, so a length per time. So that's actually important. And that hydraulic conductivity is actually also dependent on the moisture content, as we'll see in a second. So that happened to be a first experiment where people had basically, they were measuring in a tube, the discharge in that tube, and they noticed that it's only dependent on the gradient and on that hydraulic conductivity once you normalize by the area. You can think of kind of the same for trees. So you would have kind of the transpiration per unit square area, but then you need to actually multiply by the basal area, right? So when we start scaling up, we will need to actually get the total discharge at the ecosystem scale. We need to multiply by the basal area, so whatever we actually have that flux happening. Okay, and the thing that's going to be important is that hydraulic conductivity is going to be strongly dependent on moisture content. Okay, so that's something it's actually very, very nonlinear. And you tend to have much higher hydraulic content as you increase moisture content. So it means that as you get drier and drier, and that's going to be very similar in plants. We've seen that based on retention curves. Oh, sorry, on the embolism in the xylem. We'll talk about that in a second. But it's very clear that we have this very nonlinear relationship. So in dry soil, it's actually very difficult to conduct water. And that's going to be much easier in very, very humid soil. Okay, so you have this discrepancy, and that tends to be very nonlinear. And when we look at the soil plant atmosphere continuum, that nonlinearity can pop up on different at different vertical levels. So that can be important. Okay, so then we can move on to the xylem. So now we know what's going on in the soil. And basically in the xylem, so we talked about that. So we have this cohesion tension theory. And so the main idea is that basically water molecules tend to be stuck together. So they are like dipoles, and they really like each other. And so they will basically pull on the column based on some negative tension that will happen at the higher level, so basically at the leaf level due to stomata. So you will have transpiration happening here, and you will have very negative tension here in the xylem, so you're still under tension here. And you're basically going to pull the column of water based on that cohesion and tension theory. Okay, so basically what you can do is you can apply roughly the similar type of equation. So you can apply Darcy's law in the xylem here to relate basically the sap ascent to the leaves. So basically from the soil to the roots, and then the roots to the leaves. That's going to be roughly the same type of equations. Okay, so you can do that, and maybe you could argue that the meniscus approach actually is a little bit better for trees than it is for soil, but whatever. And then you can say that sap density here is going to be related to the xylem hydraulic conductivity times the gradient that we have again in hydraulic head, right? So that's going to be again the internal pressure, so the tension that we have based on cohesion tension, and you have this small gravity term. Typically, you can neglect that, but I will keep it for now. Okay. And what we'll do at first is we'll neglect storage for now, okay? And we'll say that at steady state, what will happen is that the sap that you will have here, anywhere in the soil plant atmosphere continuum, will have to be in balance with whatever transpiration will have to happen at the top, okay? And so once you integrate that from basically the soil or the roots to the leaves, what you're going to have is basically an average conductance here, so this is simplified here, times the gradient that you have in terms of tension here between the roots minus the leaves plus a small potential due to gravity. Okay, but the main point here is that you have this difference between the leaf and the roots that's actually driving and pulling that flow. Again, that cohesion tension theory. And then you have a modulation which is related to the xylem conductivity. And as we mentioned before, there's a very strong relationship with actually the tension that you have in the xylem. So that's going to actually modify the conductivity. You can think of that, it's exactly like a resistor approach, right? Where the conductivity is just the opposite of an electric circuit, right? Or an electric resistor. So that's going to tell you how conductive the xylem is. And again, you have this equality here. Okay, but there's a key trick. So again, that's maybe well known for a lot of people, especially on plant hydraulics, but I find that pretty cool if you're working on remote sensing. That's actually not obvious, I would say. So at night, there's no transpiration, or let's assume there's no transpiration. And so if you assume that there's no storage, again, we know that there's an equilibrium between the sap and transpiration. So it means that the sap has to be equal to 0. So we can go back to that equation here and say that this has to be equal to 0. So basically, the potentials here have to be equal, right? And so what this means is that the leaf water potential that you will measure at night or at midnight, as we typically, or pre-dawn as we do it typically, is going to be related to whatever is happening in the roots, and it's going to be related to basically whatever is happening in the soil close to the roots, right? And so it's actually quite nice because it's telling you that nighttime leaf water potential is actually giving you a very nice proxy for whatever is happening in the root zone. And maybe if you can observe that from space, that could give you a good trick to actually sense whatever is below ground, right? Even though that might be difficult to observe roots, as we mentioned before. Okay, so that might be in the root zone. That's a trick that I think works nicely. I mean, you have issues related to that, but whatever. Okay, so now what about that hydraulic conductivity here? It happens to be very strongly varying with the water potential itself. And that doesn't happen just at one level, but that's really a continuum, like the example we had before as a complex network from Gabby's group. So, and why is that? The reason is because water in the xylem is made as stable because it's under tension. So what will tend to happen is that you will create bubbles of air, and they will tend to actually block the flow. So basically like your heating system. So every now and then, maybe not here, but at least on the east side, you always need to basically bleed your radiator, and that's kind of the same thing, right? You're blocking up the flow because you have those bubbles that are actually really creating a very, very strong resistance to the flow. One thing that's actually quite nice, I mean, maybe less studied, but kind of interesting as well, is that ice tend to actually do the same thing. You could have those freezing crystals as well. And so drought and freezing tolerance, I mean, shares some things. I mean, there are dissimilarities, but it's not just for dryness. Freezing has actually also like similar effects. So that's kind of interesting. And what you will find is that the typical loss of conductivity, so if you normalize that hydraulic conductivity by the max, you will see that you have different types of curves, and they typically look like this variable type of function. And if you remember, very similar to what we found for trees, for soil, sorry, where we have basically this range of pore sizes. So again, you have this distribution. That's why it's not that abrupt. It's not like all of a sudden that you will entirely block the flow. You can still conduct on some of the pipes and the vessels and tracheids. Okay, so you tend to have some sort of continuum in between. So now when we think about those curves, so when we build that curve again, kind of the implicit relationship is that we are saying there's this one-to-one relationship, and that tends to be steady in time, right? In reality, that's not really the case. So when we are saying that, we are actually implicitly saying that we have instantaneous refilling, right? So we'll have that drying, and then once we get water back, we can entirely refill the xylem. So if I move back on the right-hand side here, I'm going to go back on the same curve. And the question is not that clear because it's not clear yet, or there's some debate at least, that whether refilling is actually instantaneous or not. So there's actually a little bit of a discussion on that. There can also be some memory, so that was mentioned before, on the embolized vessels, for instance. So there could be permanent damage in there as well. And there could be cell implosion as well, so you could have, again, that permanent damage. So that's an example here using staining, where you can see intact cells as red, and then uncolored, basically embolized vessels here. Okay, and you can see that maybe you could have a permanent damage system, and so you couldn't maybe go back on the same curve, and your hydraulic conductivity could be much less if that's a permanent damage in a sense. Okay, so in reality, what you have is that everything I told you is wrong, basically, and so you actually need to include storage. And so in reality, what you will have is that sap might not actually be exactly in balance with transpiration, and you have a little bit of a storage term. Okay, so typical bulk number will tell you that it basically leads to a lag of roughly 3 to 6 hours, depending on the size of the trees and the type of trees you have. And one way to look at that is you could say I can actually measure the sap basically at the basal area, so right at the bottom here, and at the top near the crown, and I can look at the difference, the phase shift between, or the time shift between those two, and that will give me a good sense of how much storage I will have in between, right? So that's basically what Phillips et al. Have done, and so you can see the basal sap flow here, and you can see the crown, or the transpiration that's driving the flow, again, as this cohesion tension theory, and you can see that, again, you have this basically time shift of a couple of hours, and that tends to still happen at night because you have this refilling, as we call it, of the xylem happening at night. So even though transpiration has stopped, you can actually still get some sap getting in there so that you can actually refill your system. And that can be annoying if you want to look at that from space, different story. And there's a very clear link between that lag here between basal sap flow, so the peak here and peak in transpiration, and how much capacitance. So you can think of that again like an electric circuit, like what is the capacitance of your RC circuit and how much you can actually store. Okay, so there's a very clear relationship, and that makes sense, basically. Okay, so now if we move to the top and we move to the leaves, what we'll have is we have basically leaf gas exchange, and that's actually very important because that's where you're going to connect water and the carbon cycle there. So you're going to pick up CO2 and for photosynthesis, and you're going to basically leave some water out, which is basically transpiration. And stomata are going to regulate that, and they will tend to open and close based on different stresses. And so what's going to happen is you're going to have some strong regulation, and water is going to be very important here for that stomata regulation, for those stomata regulations. And again, what you will see is that leaf water potential here, so at the top of the leaves, or typically at the petiole level, will actually have a very strong impact on stomata conductance. And so those are two different species here, where you can see that species here is going to be, those are pinion pines, where they tend to have a very, very abrupt change here in terms of stomata conductance as a function of leaf water potential. And then some other species next to it where you can see actually a weaker dependence here. Okay, so that can actually vary even in your, at the landscape level from species to species. Now, how do we typically model that? So transpiration is basically a diffusive flux, at least so basically that's Fick's law, saying that you have transpiration is going to be again some diffusion, which is the conductance of the stomata, times the gradient that you have between the vapor pressure within the leaf and outside of the leaf. Same thing for growth primary production. That's going to be a stomata conductance times the difference in ambient carbon and in intercellular carbon. So same thing, that's going to be a diffusion process. Now, the thing is that stomata conductance is going to be regulated by different things. And in particular, people at least, so that's more in the model world, let's say, are modeling that as a function of vapor pressure deficit and the leaf water potential or soil water potential. So they are trying to relate the stomata closure and opening to things that are actually stressing out the plant in terms of water stress. So basically water pressure deficit, which is the dryness of the air, and then some indicator of the dryness within the plant. So it could be leaf water potential or soil water potential. And you have many different formulations. I mean, you have many different flavors. So in terms of the vapor pressure deficit dependence, so if you assume that you have well saturated soil, so you don't have any stress due to to soil moisture in that case, typically what we believe now is that stomatal conductance is going to be related to photosynthesis and also to vapor pressure deficit to the square root, basically the square root of vapor pressure deficit. And then, so that's what we call the Medlin model, but it's actually following up a long story of those optimal models, starting with Cohen and Farquhar. Gabby has been working a fair amount of that, Kim as well. But the main point is that this is saying that you have this square root dependence on vapor pressure deficit. So that's basically almost considered state of the art these days. And you also have this Ball and Berry model that's saying it's actually going to be a relative humidity that's stressing out the plant and not vapor pressure deficits. And you could say it doesn't matter, but I would say it matters a lot, because as you start moving into a warmer climate, relative humidity is actually dropping a little. So there's some really nice paper by Byrne and O'Gorman showing that relative humidity over continents is actually dropping a little. But vapor pressure deficit is going through the roof because temperature is increasing and you have this exponential dependence of closest collapse on vapor pressure deficit. So which one is correct is actually that's going to be a big deal, in terms of the response of stomata. Here are some other things that are a little bit more sophisticated and maybe more physically based, like the idea of Sperry, which is based on supply and demand for that regulation of conductance, or the idea of Wolf and Bill Andrek here on basically using a carbon maximization theory based on different constraints to actually look at those things. And again, so those are different ideas to actually look and try to implement ways that the way stomata will actually respond to either the dryness of the air or basically dryness also in the soil. But in reality, when you start looking at models, it's basically very, very ad hoc the way people implement that in models. And they don't even know where they have to put that stress. Some people actually put that in terms of a regulation of the maximum conductance. Some people put that in terms of VC max, so maximum carboxylation. So it's very unclear where that stress is actually occurring in the plant. So that's still very much an open debate, I would say. And that's really something we need to address, actually. OK, so now when we start thinking, that will be just at let's say, a single tree or single plant level. So we have that stress basically happening at the leaf level that we mentioned, and we have that xylem embolism or cavitation happening on the right-hand side. And we have basically those two competing stresses happening at the same time. And in fact, there's an interplay between those two, as we discussed. Now, what can happen is that you can have these, you can have a spectrum of different responses, but one of which is actually this very isohydric type of behavior. And by that, what we just mean is that leaf water potential is going to be very, very steady when we actually record that, okay, across different time scales and during, say, a dry down. It's actually very unclear how that's actually very defined in the first place, but that's a different story. And then you have those more anisohydric type of species where actually the leaf water potential, which is recorded here during different dry downs, are actually going to vary substantially. Okay, and so those are very dramatic differences for two different species actually living and coexisting in the same landscape. So those are pinyon pines at the top and junipers at the bottom. And they basically coexist within the same landscape, so here in New Mexico. And when we look at the stomatal conductance, so those are the two examples we had before. So the ones that had a very sharp drop in terms of stomatal conductance as a function of leaf water potential was the more isohydric species here. And then the anisohydric was the one that was actually going a little bit softer into the regulation. Okay, so those things, might actually tell you a lot in terms of the water strategies that they are using. So why is that important? It means that that's going to have an impact in terms of the water fluxes, but also in terms of the carbon fluxes, again, through the stomata that we have. So if you record the sap flow here as a function of a dry down here, you're going to see that the isohydric species here in white circle are going to have and see a much stronger drop in terms of the sap flow during a dry down. And the anisohydric species are going to see a much weaker response to a dry down. So they can maintain a fair amount of photosynthesis and a fair amount of transpiration. So relatively different type of response to a drought. And you can see that, again, vapor pressure deficit here is going through the roof. And you can see the almost complete stomata shutdown in that case of the isohydric species. And sorry, I apologize for my voice. I have a pretty bad cold. OK, so Now the question is, when we start thinking of, so that's more at a personal level here, but when we start thinking of that leaf water potential and the different timescales you have, it's very clear that you have diurnal to seasonal variations. So if you look back at that plot, here the leaf water potential variations that you had were not just on the daily timescale, so you have midday and pre-dawn, so you can see substantial drop here. But you can see that you also have very substantial seasonal variations as well. So it seems that physiology might actually affect both of them. Now the question is that on seasonal timescale, the root depth or whatever that is, I mean that could also be the area extent of the roots, is also going to regulate the water potential as we mentioned before. So if you remember, and again we believe for the sake of the argument that storage is going to be small, we know that at night the root water potential has to be in equilibrium with the leaf water potential, so it means that the root water potential has to be very important as well. So it means that the root depth has to be also very important on seasonal timescales. Okay, so it means that it's not just about physiology here, but it also means that there might also be an interplay with basically the rooting system as well when we start looking at longer timescales. Okay, and that's basically a paper we submitted with Alex and a postdoc in my group, where you can actually start looking at that maybe at the global scale, maybe trying to think, could there be some coordination between rooting depths and hydraulic conductance as well? So maybe those two could actually be working in different places. So in that case, you could have relatively low rooting depths, and you could have relatively high hydraulic conductance. So you can do that maybe using remote sensing data. Okay, so how is that implemented in models? Because that was the title of the talk. There are a couple of examples now. So that one example is actually by Daniel Kennedy, he's a student in my group, going to graduate pretty soon. And there are some other examples, like in the Joules model now, where basically what they are trying to do is using that porous medium type of analogy in the soil plant atmosphere continuum, and they plug that, and then they have again a relatively ad hoc, and we have a relatively ad hoc way of formulating the impact on the conductance at the leaf level. And that's again relatively ad hoc. We had, in that case, different layers in the soil. We had also shaded leaves and sunlit leaves, maybe related to Gabby's question from before. So you can also have different vapor pressure deficits here on those different types of leaves, because that's, again, the leaf level vapor pressure deficit, which is very dependent on radiation. And what you could see is that you can have, for instance, then you can have the evolution of the rooting system water potential, and also the sun leaf shaded and shaded leaves water potential as a function of time. So that's an example here using actually Patrick's site and the one he showed you before, where you have the ambient site and the through-fall experiment on the right-hand side, and you can see the impact in terms of the rooting system, but also in terms of within the plant leaf water potential. You can look at that as a function of time. So again, you can see that very strong seasonal dependence of midday and pre-dawn water potential, and you can see also the very strong diurnal variations as well, as compared to the soil, which tends to be very smooth, right? I mean, there's barely any variation compared to what happens within the soil. And that's very directly connected to photosynthesis as well, because that's basically how that's implemented in model, and that makes sense. Okay, so basically once you get your photosynthesis going, you can have basically some carbohydrates, and what you like to do is basically allocate that for growth, respiration, and basically storage. And so that's typically done through the phloem, which is basically how you bring those things down to wherever that's needed. And the idea here is that what will happen is that as you start building up carbohydrates, you will try to increase the osmotic pressure, or tension in that case, and that's going to create a pressure flow, basically as very much like a membrane that's going to drive the flow from the xylem to the phloem, and then it's going to drive the flow down the phloem in that case. And that's going to drive basically the allocation or from the top to wherever that's needed for the different things, again, for growth, respiration, and storage. That theory, so that's called Munch hypothesis, which was built like a long time ago, like almost like a century ago by a German scientist. And the theory has been shown to have some issues when you start thinking of long distances, because you can have some friction here in those sieve plates here that are actually might be too resistive to the flow. So it seems that maybe over long distances that theory may not work so well. When we start thinking about the phloem, so those are some nice results by Paolo Bittencourt. He's in Rafael Oliveira, who's in the room here. And he had some nice measurements of the xylem swelling during the day and also the phloem swelling during the day in Manaus, or near Manaus at K34. So that's a tower in the middle of the Amazon. And those are for 2 different species here. So as a function of time, after a couple of rain events here that are depicted in black here. And what's kind of interesting is we can see huge species-to-species variations here in terms of the variation you can get in terms of the xylem response and the swelling in response to basically some moistening here, but also in terms of the response that you will get in the phloem. So for instance, the phloem of that species here is barely changing after the rain pulse that we are getting here, whereas this one is actually getting a huge increase. So there seems to be a lot more going on in terms of the phloem response. Okay. And so that type of variation seems to be very important. And so the question is, how does that scale up to the scale of the ecosystem and to the landscape scale? So again, when we summarize that, so it seems that on daily time scale, we have this xylem and phloem response and leaf gas exchange. And on monthly time scale, you have basically these, plus you have also this rooting depth modulation. And you also have growth that can also be something that can be really annoying when you start thinking about remote sensing data. Okay? And so the question is, again, you will have this increase in biomass, but also moisture can also be changing. So you need to actually normalize that somehow. So that can be, you can have those covariing factors on very, very similar timescale, and that's a very big challenge to actually start disconnecting the different things. And that's one example here, using, for instance, vegetation optical depths in black, so just the seasonal cycle of that, which is related to total moisture content. And then here you would have some indicator of biomass, so enhanced vegetation index. You can see that they are very much in phase, so you can very much see the growth. So how can you actually best normalize that so you can start thinking of relative water content and maybe leaf water potential? So that's an open question, I would say. You can also look at longer time scales in that case. So that's one example here from a student in my group where we looked at interannual time scales. And it's quite well known that, so those are tree rings here, so looking at different years. And it's quite well known that when you have a dry year, you will have basically a smaller ring, and then you will have a wider ring when you have basically a wet year. But you can think of that as maybe that could have an effect as well on the water cycle, right? Because as you start modifying your plant hydraulics here, you're going to modify the area, but you might also change the structure of those cells as well. So maybe that could actually have a feedback on interannual timescale. So maybe if you get dry the following year, you might not respond the same way. So that's basically what we tested, looking at some. You can actually count those cells. So that's you have some software to do that, but that's still really painful, and don't advise any PhD student to actually do that. And you can start looking at some of the statistics here as a function of drying. So you can look at, for instance, leaf water potential as a function of time. So you can see that you had a dry year here that was very abrupt, and different kind of wetting experiments. So the blue experiment is an irrigated field for pinyon pines, and the red is a very dry field. And then you can start looking at cell wall thickness, for instance, and looking at, you can see that drying that's actually happening in the dry experiments. Or you could look at some indicator of cell implosion. You know, what is the risk that we have for implosion and maybe the impact that we will have on xylem. It's very clear in that case that the dry site is actually seeing a very strong impact. So it seems that, you know, the longer the dryness lasts, the more impact you will see, and that will actually have a feedback on that water cycle on longer time scale. So it's not just about the snapshot, but you could have seasonal and also interannual time scales. So not just about temporal scale, but you also have those spatial scales. So that's just the last slide. So the trouble that we have is that when we start thinking of remote sensing, we have to basically integrate a lot of what we are seeing at the landscape level. And we have basically this huge diversity in terms of species that we are observing with many different characteristics in terms of height, in terms of traits. And the question is also that we have huge gradients as well in terms of the microclimate that we will experience. So even within a tree itself, at the top of the tree, you might have very intense light. At the bottom, it can be relatively shaded. And you will have very strong water limitation as well. So at the top, you can have very low water potential and very high water potential at the top. And so basically, water limitation might actually build up as you move up into a tree. In the meantime, you also have one thing that's going to be very important so that you can actually carry scalars, so moisture and CO2, is actually turbulence as well. So you can have very intense turbulence at the top and very limited turbulence at the bottom because that's very limited by the lack of by the effect of the drag of the canopy at the top. So basically, turbulence, light, and water, and also nutrients might actually be changing dramatically in space and also maybe in time. So that's also maybe a big challenge when we start thinking of what is that we are actually observing at the scale of a remote sensing pixel. So with that, I'll finish. And thank you.